how does it affect us? The light from the rising sun is always a source of inspiration and wonder. Throughout the ages, men have associated light with truth and knowledge, darkness with ignorance and evil. And although even today there are questions about what light is, we do know a great deal about how it behaves. This is the science of optics. We know that light is a form of radiant energy traveling through space at the amazing speed of about 186,000 miles per second and capable of producing the sensation of sight. You are using your sight to see that Sandy has found a good spot to cast. Like those ripples in the water, light radiates from its source in a pattern of expanding waves. Light waves radiate in all directions in straight lines, sometimes called rays. However, it is easier to study light in terms of a single ray. Just as a stone skips off water, light rays bounce. This is called reflection. A smooth surface gives regular reflection, but a rough surface reflects the light in many directions. We call this irregular or diffuse reflection. It is the light reflected diffusely from rocks, trees, and such objects that enables us to see these things. Reflection, Bud thought. That's what they were talking about after their fishing yesterday. Sandy and Bud like to have simple versions of demonstrations they've seen in the science lab at school. The bright sun pouring in through a tiny hole in the tent provided a ray of light, and with a few simple gadgets, they could see how light behaves. A shiny piece of metal made a mirror. What happens when light bounces off a reflecting surface like this? They could see the angle of the reflected beam as the mirror was rotated. Sandy showed Bud the relation between the incoming light and the reflected. Regardless of the size of the angle, the law of reflection is the same. The angle of incidence, that is, the angle at which a ray strikes the surface, is equal to the angle of reflection, the angle at which it leaves. This principle is true not only for flat or plane mirrors, but also in a slightly different way with curved mirrors. At different parts of the curve, the rays are reflected at different angles. A concave mirror converges the rays, while a convex mirror spreads or diverges them. Sandy said he could always remember concave by thinking of a sort of a cave, hollow. Convex is the other way. These principles are used in the trick mirrors you often see in amusement parks. Bud makes a more practical use of a curved mirror when following his hobby of photography. The interior surface of this reflector is curved so that the light is directed towards the picture-taking area. Well, that's what happens when light is reflected from things. Now what happens when light goes through things? Well, it appears to go right through this glass. Actually, however, while light is passing through glass, it slows down to about 2/3 of its normal speed. In the air again, it resumes. When the rays enter the glass at an angle, this slowing down and speeding up causes refraction. Rays that enter first slow down first, causing the beam to bend. They also leave the glass first and speed up first, causing the beam to bend back parallel to its original direction, but offset or shifted. When Sandy handed Bud a glass prism, he could see how the sloping sides changed the direction of the beam. Back in the boat, Bud could see refraction as he dipped an oar. Because light coming from the underwater parts of the oar is speeded up when it comes out, the rays are bent, and so make the oar appear to be bent. Right now, Sandy isn't concerned with refraction. He's got a bite. But Bud is going to use refraction in the camera lens to get a picture of this. Just as he was telling Sandy yesterday, light is refracted in a lens. A lens is really a sort of prism with curved sides. The light rays are refracted or bent towards a thick part of the lens. The point at which the rays meet is called the focal point, and the plane in which called the focal plane. A camera is simply a light-tight box with a lens. At the focal plane of that lens is a sheet of light-sensitive film. This is how an image is formed by light rays. Light reflected from, say, the nose of the fish enters the lens where it is refracted and brought into focus on the film. Light from this point on the nose focuses at this point on the film. The same thing happens to the light from a point on the tail and from every other point in the picture area. So it all adds up to an image on the film, which becomes a permanent photographic souvenir and printed in Bud's darkroom. Snyder didn't think the little print did the fish justice, so Bud offered to make him a big one with his enlarger. He explained that the enlarger uses a lens and the same principles of refraction as the camera, except in reverse. Light is projected through the negative and focuses a larger sized image on the easel. But Sandy could not see his picture at all if it were not for another marvelous optical instrument, the human eye. Like a camera, the eye has a lens which focuses light rays on the retina. When a person's eyes are unable to focus clearly, his defect is corrected by eyeglasses, lenses which refract the light so the image is focused sharply. A pair of binoculars can be added to the eye's optical system to enable us to see distant objects clearly. A microscope does the same thing for small objects, while the observatory telescope enables us to look into outer space. Did you ever stop to think about the many uses we make of light, the everyday things around us, and the less obvious applications? Motion pictures, television, the electric eye? You can demonstrate for yourself, just as Bud and Sandy did in their own way, many things about reflection from plane and curved mirrors, and about refraction, and what that means to lenses and to the whole science of optics. And there's a great deal more you will find interesting about the nature of light. For instance, do you know the parts played in this scene by the reflection and refraction of light?
If you remember, when we were doing mirrors, we had convex, concave, and plane mirrors. There are no plane lenses. That's just a pane of glass, like a window, that doesn't bend the light because the glass is just flat. So the image isn't distorted in plain, flat glass. But we do have converging convex lenses and diverging or concave lenses, just like we had convex and concave mirrors.
Lenses. Most of us are familiar with lenses, convex lens or converging lens. An optical glass sphere can be cut in the required manner to obtain convex lenses. There are three types of convex lenses: the concavo-convex, the double-convex, and the plano-convex. Convex lenses are thicker in the center and become thinner at the edges as shown here. Rays of light passing through a convex lens converge to one point after refraction. This is the reason why a convex lens is also called a converging lens.
And we're going to start with convex lenses, and there's three rules, and they're basically the same for convex and concave lenses. They involve drawing rays from the object to the center of the lens and then bending it towards or away from the focal point. For convex lenses, the first rule is that you're going to start with a ray parallel to the principal axis, just like we did with mirrors. And when it gets to the center of the lens, it's going to be bent through the focal point. And this is an actual light ray bending and being focused on that at that focal distance. The second rule is we're going to draw a ray straight through the center of the lens, the optical center, and it doesn't get bent. It falls on the lens flat, so it doesn't, no part of the wave hits the lens before any other part of the wave, so it doesn't get bent. And we can already see that these two rays of light cross at one point. But we'll go ahead and draw the third ray and see that it crosses at the same point as the first two. The third rule is it's the opposite of the first rule. We're going to draw a ray through the secondary focal point, F prime, to the center of the lens, where it will be bent parallel to the principal axis. And you see that the three rays of light meet in one spot, and since we started drawing the ray from the top of this lady's head, then where they meet is still the top of her head. Her feet are still on the principal axis, and this is our image. Okay. And obviously we need to look that there's something different about this image as compared to the object. The woman's image is smaller, inverted from the original object, and it is also real. And again, just like with a mirror, you can tell that the image is real if it is actual light rays converging at one spot. They're not light rays that your brain has to trace back to somewhere that it thought they came from, but actual light waves crossing in one spot. Okay? We can categorize lenses by the images they form, whether they form smaller, same size, or larger, whether they're upright or inverted, and whether they're real or virtual, just like we did with mirrors. This one is for a little illustration for convex lenses. You can see that when the object starts beyond 2f and you move it in, the image gets bigger and bigger and bigger until right at the focal point the image disappears and it starts making virtual large images. You can see here right at the focal point the light rays are parallel, don't form an image just for an instant, and then it starts forming virtual images if the object is in between the focal point and the mirror or the lens. Now let's define some parts of this anatomy of lenses and ray diagrams that we can measure. Okay. The first thing we can measure is the focal length, and that is from the center of the mirror out to the focal point. It's usually measured in centimeters. The object distance, also from the center of the lens out to the object. The image distance, from the center of the lens to the image. The object height, which is from the principal object to the top of the object. and the image height, that is from the principal axis down to the height of the image. And little things about this, there are some rules, like our image here is below the principal axis, so it's going to have a negative height. The object is above the principal axis, so it's going to have a positive height. And we'll talk a little bit later about the conventions for deciding whether or not an image distance or object distance is positive or negative. It depends on whether it's real or virtual. But we'll deal with that when we draw ray diagrams. Okay, now for concave lenses. The rules are basically the same. We are going to start with a ray parallel to the principal axis to the center of the lens. But for a diverging or concave lens, it gets bent away from the focal point. But it gets bent away from the focal point in a straight line. So this ray cannot converge with another ray because the concave lenses diverge. They send all light rays away from each other in different angles. The second one is just like it was with a convex. It's straight. It's from the same point straight through the center of the lens, the optical center, without being bent. And again, we can already see that these rays are crossing at a certain point, a virtual ray and a real ray. And so that's where our image is going to be, but we'll go ahead and draw the third ray, which is through the focal point. And that's the focal point on the other side for a diverging lens. It's pointed at the focal point and it gets bent parallel. And we can see that they all three cross at the same place. And this image is smaller, upright, and virtual. And it turns out that diverging lenses only form virtual, upright images.
This is going to be a practice problem showing a ray diagram using a convex lens. As we get started here, you can see that we have the object represented by the red arrow on the left side of your screen. And we're going to draw three rays, three lines that will go through the lens, will be converged to a single spot, and then we'll be able to see what happens to the image as it passes through this convex lens from this distance away from the lens. So the first line that we're going to use, so the first ray that we make goes from the object parallel to the principal axis towards the lens. So we're going to use a black line to represent this first one from the object parallel to the principal axis towards the lens. It hits the midpoint of the lens there, and it's going to be refracted. As it gets refracted through this convex lens, it's going to be converged and sent from the lens out through the back focal point. So we go from the lens through the back focal point, and we just keep on going through there. We'll use a little arrow on the end here to show that it's passing through in that direction. So that's the first line that we draw. The second line that we're going to draw is going to be using a different color. It goes from the object through the front focus towards the lens. From the object through the front focus towards the lens. Once it hits the lens, it goes out parallel to the principal axis. So again, being converged, bent towards the normal, out parallel. And we'll put an arrow on the end of that one. So we have our two lines. You can actually see our intersection already, but we'll do the third line just to make sure that we are on the right track here. We'll just go straight through the center, from the object, right through the center. You can see all three of those rays will converge at that point there. So if we look at the three rays, we can see our intersection. We'll use red here. Our intersection takes place right there. We'll go ahead and we'll draw our image. Alright, and there's our new arrow. And so we can describe this. Remember how we describe them? We first of all would say that it is going to be inverted. INV for inverted because it is now upside down. We can also say that it is real, because all three lines are being intersected without having to trace them backwards. And then finally, it would be magnified. Showing a ray diagram using a concave lens. We can see that we have our image, our object with the shown with the black arrow on the left side of your screen. We're going to draw three rays that will represent what will happen to this, the image of this object as it's being refracted, as it's being passed through this concave lens. So from the object, parallel to the principal axis, I guess we're using orange, that's okay. From the object parallel to the principal axis towards the lens. Now, once it gets to the lens, it goes out in line with the front focus. Now, if we have our front focus, which is this line right here, we need to use that to generate our line that's going out. Remember, this is a diverging lens, so it's going to be bent away from the principal axis. And so we use the same line that there would be from the front focus, and we head it out in the same direction. Now, my lines might not be perfect, but I think that's lined up pretty well as we go in line with the front focus. And we're going to go ahead and put an arrow on the end of that one because that's the one that's being transmitted through. So that's the first line that we draw using our rules for the ray diagram. The second line, go towards it. Alright, now it's not going to make there because it's going to get refracted. It goes towards that back focal point. Once it hits the lens, as it's being refracted, it gets sent out parallel to the principal axis. There, parallel to the principal axis. From the object through the middle of the lens and the principal axis, it just goes head straight on out. So right through the middle and to the other side. We'll put our arrow on the end of that one. Now, as we see our three lines that are being refracted passing through the lens, they're not going to intersect on the right side of the lens. They're going to have to be taken backwards and extended back to see where they would intersect on the left side. So right away we know that this is going to be a virtual image because it's not intersecting on the right side. It's going to be intersecting on the left. And to kind of make that a little bit more clear, I'm going to go ahead and get rid of these lines that we don't have to deal with. So we'll get rid of these. When we extend our lines backwards here, we'll just use black for all of them now. This is going to be extended back in this direction. The orange one will be extended back in this direction. And what we'll end up seeing is that our intersection is going to take place on this side of the lens, right about there. Put our new arrow right where that intersection takes place. Alright, so let's describe our new image. Our new image is going to be, first of all, we said virtual. Alright, it's going to be virtual because it is, you have to trace those lines backwards. Second of all, we know it's smaller, so we're going to say that it is diminished. Put DIM for diminished. And then it is also upright because it is it's in the same, has the same orientation as the original. So virtual, diminished, and upright when you have a concave lens.